A couple of weeks ago, I passed my PhD qualifying exam in analysis. This exam covered two topics, real analysis and complex analysis. And we split the test into 2 days. So they allowed us to take the real part on Wednesday and the complex part on Friday. And in the video, Happy Grad Student, I talked about my experiences on both of those days. So if you're interested in knowing how it went, I recommend watching that video. Yeah, the furnace, or not furnace, but air conditioner next to me decided to turn on at the most inopportune moment, so I apologize. But I decided in this video to show the exam. So I said in that video that if the test was uploaded to the university website, then I would show you what the test looks like. So I'm going to do that now. And so the first one that we're looking at is the real analysis part. And so you can see this was the actual paper that I had during the exam. They let me take it. There was a couple copies. They don't really care if you take one because they don't reuse these. So the first problem is always a theorem. The theorem that they chose was the Vicali covering lemma, specifically the finite version. And it says that for every finite family of open balls in a metric space, one can choose a subfamily of balls such that the balls in the subfamily are pairwise disjoint, provided that you expand each radius by a factor of 3. So essentially, you have some balls, you pick some of them, you have to choose them specifically. Of the balls that you've chosen, you expand the radius to 3 times, such that this property holds here. Which means that if you union all the balls that were in the original family, they will be a subset of the union of the balls that you chose that have 3 times bigger radius. The reason why this lemma is interesting is because it is used in the Hardy-Littlewood maximal function? Or is it the inequality? It's the weak type bound, the Hardy-Littlewood inequality that's used for the maximal function. I have to look it up, but I know I can picture where it's used in what theorem because I practiced that theorem a bunch. The name escapes me at the moment, but I know it's Hardy and Littlewood. Question number 2. Let AK be a fixed sequence of positive numbers. Let FK map from the interval 0 to 1 to positive real numbers. It is non-negative Borel measurable, satisfying the following inequality. The integral of the function over the space is bounded above by AK of the sequence you chose. Part A. Show that if the sum of the sequence terms is finite, then the functions tend to 0 almost everywhere, pointwise, with respect to the Lebesgue measure. Part B. Show that if the sum diverges, then there exists a sequence of non-negative functions as above, such that for every x in the unit interval, the sequence fkx does not tend to 0 as k tends toward infinity. Okay, so what I've noticed is that in recent years that the guy that likes to write these tests, problem 1 is always a theorem, but problem 2 is always a two-parter, where part A is like under some conditions show that some result holds, which is that kind of describes every, analysis problem more or less. But he words it in such a way that for part B, he says, okay, now tweak the assumption of A just a tiny bit, and then show that by counterexample that part A doesn't always happen. So I've noticed that he did it this time. He did it the practice test that I showed on my channel once before, and then the qualifying exam that bodied me, which is a video on my channel. He also did that there as well. So question 2 seems to be a two-parter that's built like that, at least when he likes to write them. Problem number 3, let f be a continuous function between Rn and Rm, and let U be an open set. Show that the image of U is a Borel set. And I circled this one, and there's a reason why. I'll talk about that later, so let's just go through the rest of these first. The functions Gn from R to R are Borel measurable. It is known that Gn tends to 0 in Lebesgue measure. As n tends toward infinity, we know that the integral of Gn squared dm is bounded above by 1. Let f be a Borel measurable function such that the integral of f squared is finite. Show that the integral of f Gn dm tends to 0 as n tends toward infinity. Okay. Question 5. Let an and bn be a sequence. of real numbers. Given that the series of an, so you add up all the an's, converge conditionally, and bn is between n and n plus the square root of n, show that the series an over bn converges conditionally as well. All right, so just to comment on this test. Problem number 1 and problem number 4, I knew immediately how to do it when I read it. So these two I definitely got. Question 2, part A, I definitely got as well. Knew immediately how to do it. I screwed up number 5. The tick mark meant I had something written for it, but I realized that my answer did not work, and so I decided to return to it at the very end if I had time. Unfortunately, I ran out of time and I did not have an answer for question 5. So question 5 I missed. Had I been given more time, I may have been able to prove it, but I haven't even looked at it since the test was over. But I didn't do 5 right. Well, I didn't have anything written, so obviously I didn't do it right. But I did do 4, I did do 2A, and I did 1. Those were all correct. 2B and number 3. When I read 2B and number 3, we were already in like hour 7 of this test, and I knew that I probably only had enough time before getting kicked out to solve one of them. And reading B, I knew that I could probably do it. So I spent maybe another 2 hours trying to come up with some simple example. And the thing that bugged me about it is that I knew what the example had to look like. I knew that it had to be like, it was a common example that we had seen in the class a million times over. But I just couldn't get my example to work. And I don't really know why the example wasn't coming to me, because I even went up to the proctor who wrote the test and talked to him about it. It's just, he's like, yeah, that's what you got to do. You just got to write it down right. And I'm like, well, I can't. I don't know why. I don't know why. 2B bugged me. Like, it just wouldn't come to me, and I knew what the answer had to look like. It's just, I couldn't write it. In hindsight, I wish I had given up on B and done number 3 instead, because the answer that I had submitted for number 3 was really, 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 really close to the right answer. And then after I turned in my test, which was hour 10, I believe, I went home, I got back to my place, I tried to decompress, not think about the test, watch a YouTube video, eat dinner, and I just couldn't help but not think about number 3. So I I closed YouTube, put away my food, got out a sheet of paper, and I wrote it up. And I think in about 3 minutes, I solved it. And I looked at my solution. I was like, there's got to be something wrong with it. This can't be the answer. And I thought about it, and I thought about it. And the more I thought about it, the more I realized I had done it correctly. Or at least I was really convinced that I was. And I called my family, and I told them about it, and I was upset because it was so close. Like, what I had written was so close to what was real. Like, had I just given up on B and done 3, then I would have had 1, half of 2, 3, and 4 solved, which was pretty much all I could ever hope for. So I went to bed, couldn't sleep, woke up at 4 o'clock in the morning, opened up a Word document, typed up my solution, and I emailed it to him. And then I didn't even want to check my email until after it was all over. And then when it was all over, he emailed me back. He goes, yep, that's the way you want to do it. Now, whether or not he actually included it in my score at the very end, because technically I'd already gone home, he probably did not. I would be very surprised if he did, because it's not, I mean, it's reasonable, right? The test is already over. Why would you count it? But there was a slim possibility that he would have. So that was all that I needed in order to email it to him. So that's kind of how I felt, you know, towards the end of that test day. Is like, I really wish I had given up on B and done 3 instead. Number 5, you know, I can't really complain. I mean, had I been given a couple more hours, maybe I would have solved it, but I was really just hoping for 3 out of the 5. That's really all I wanted. Anyway, So that was the real analysis test. This was the complex analysis test. And you can see I kind of wrote down what needed to be used to solve each of them. Problem number 1, let the sum an zn converge to some non-zero complex number. Prove that the sum an zn converges uniformly in the following disk with r less than the absolute value of z0. So this is supposed to be a theorem from the Alfors book. And I believe it was Abel's theorem or Hadamard's theorem. I don't know what you want to call it. I think in the Alfors book it's called Abel's theorem. And it's a 3-part theorem, and this is just one of the 3 parts. And I vaguely remembered how to do it. I looked over it a few times. And I remember that Weierstrass's m-test is in there. And I think Hadamard's formula is also in there. And the long story short is I did not successfully remember how to prove it. But I do remember the big things that were used in the proof, like the m-test and Hadamard's formula. And so I know I screwed up 1. I don't know how much partial credit he would have given me. Probably not much. Maybe like 3 out of 10 for what I've written. And after the test was over, I looked up Hadamard's, or not Hadamard's, but Abel's theorem in the Alfors book. And I was like in the neighborhood, but I was not close to it, so I probably did not get very many points for it at all. But I did remember the m-test, and I did remember Hadamard's formula. I don't know how much that's worth, though. Okay, questions 2, 3, 4, and 5. I got full credit on all of those. So this test really did save my butt on test day. So then remember, this test took 6 hours. I think I was done at hour 3, and I spent another 3 hours just checking my work. So question 2 is a contour integral. You have a circle centered at 0 of radius 1, positively oriented. It's not mentioned here, but it's assumed that the orientation is positive because it's always positive. Usually. Is usually positive. It'd be very weird if they said, okay, this is oriented negatively. You never really read it. And so you have to evaluate what this integral is. So what you want to use is Richet's theorem. You want to look in the, well, actually you need to do change of variables first. So you need to do a change of variables, and then you need to essentially factor the denominator and apply Richet's theorem. So after you apply Richet's theorem, you'll show that one of the terms in the factors does not have a 0 inside this circle, essentially, which means that all of the integral comes from, you need to use residue theory is what I'm trying to say. After you apply Richet's theorem, you need to apply residue theory and show that you have a singularity at 0, in which case you just have to, you know, take 2 pi I and multiply by the limit as z tends to 0 of your integrand, and eventually you'll get the answer. So there's 3 parts to problem number 2. You need to do the change of variables, you need to apply Richet's theorem, and then you need to finish it up with residue theory. And that's number 2. And I remember at my answer at the very end it was the exact answer, but minus. Like I had a minus there. I had this minus floating around. And my proctor was like, well, where is this minus coming from? Until eventually we found out that it comes from the change of variables. Because when you do the change of variables, instead of positive orientation, you'll have negative orientation. So in order to get the right answer, when you substitute in that negative actually becomes positive if you spin the circle around the other way. I didn't explain that very well, but that's just how it happened. You take a negative, multiply by a negative, get positive. But it didn't end up counting against me. We corrected it, and I got full credit. Problem 3, map the region between this circle and that circle to the half plane. And you can see my notes I've written at the side. This is too easy. I wrote too easy because this was a homework problem that the instructor gave, and I collected all of his homework. And this one wasn't too bad. I had done this one before. I believe this was the first one I did. This one, because I read it and I was like, oh, I remember that for homework. And I probably did it in like 5 minutes. It wasn't that bad. By the way, number 2. This was a type of integral that I did not practice right before the test. And I remember like the night before we took the test, I remembered integrals like this. And I was like, crap, I didn't practice those. But I kind of remembered what the trick was, that you needed to use Richet's theorem. so that when this test was plopped down in front of me, I read through the problems, and I was kind of scared for a second. I was like, oh crap, I don't really remember these. But I had to calm down. I was like, okay, if I just spend some time thinking about it a little bit, then I would remember how to do it. And I did. So for number 2, I remember it's like, okay, we can use Richet's, yada yada, and then everything just happened nicely. So it started out bad, but as time went on, I realized this test wasn't that bad. Problem 4, show that any 4 distinct points can be carried by a fractional linear map to positions 1, -1k, -k, where the value of k depends on the points. And you can see over the side I wrote y with 3 exclamation marks and 3 question marks. And that's because this was a homework problem that he gave, and this was the one that I kept avoiding. I didn't like this problem for some reason. I didn't want to deal with it. I think I did it like a week before the test, because I texted a friend of mine. He's like, can you do this problem? Because I don't like this problem. And he sent me a solution. I don't really think his solution was correct, though. Like, there was just something about it that just didn't make sense. And when I sat down and looked at this, and I was like, okay, I know that you need to use the cross ratio. So I set up the cross ratio, plugged some stuff in. I talked about this in the video, by the way, Happy Grad Student, where I actually solved this problem, and I detail like how much each part of the problem was worth, because I had this bit, but then there was this little bit at the end that I didn't have. And without that little bit at the end, I've only gotten 60% of the problem correct. So if you're interested in the solution for 4, it's in that video. But I was able to do it. It was the last problem I did for this test. And then number 5, let D be the unit disk. F is analytic from D to D. F of 0 is 0. Prove that every Z in D, one has this inequality. So number 5 caught my attention immediately. I did this one first, but this one caught my attention because when I saw this and I saw that, I immediately thought of Schwarz's lemma. And so I tried using Schwarz's lemma, but it didn't work immediately. Like, I got something close. I was missing this squared at the end. So I was like, oh man, Schwarz didn't work. And there have been a number of cases where I saw this assumption, and I was like, oh, we got to use Schwarz's lemma, but Schwarz's lemma is not used actually. So I sat and I got upset, and I was like, I don't know if I can do this. So I moved on to something else. I think the order in which I did these was like maybe 3, 2, 4, and then 5. I can't remember if it was 4, then 5, or 5, then 4. But I know number 1 was the last one I did. Because I could definitely, because I knew which one this was in the textbook, and I wasn't sure, I was pretty sure I couldn't do it. But I could do 2 through 5 if I tried hard enough. So number 5, I remember he gave us a hint, like in the classroom. He goes, and his hint wasn't very descriptive. It was like, remember the proof of Schwarz's lemma. And then he just walked out. So I was like, okay, how do you prove Schwarz's lemma? So I got out a second secret sheet of paper, proved Schwarz's lemma, looked at the proof, and I was like, okay, how can we use this? And I stared at it long enough, and then I realized, like, if you write down the Taylor series expansion of F, because it's analytic, you can do that. Some nice things happen here. When you add these two together, you get some nice cancellation, and then you can define a specific function that is based on this. If I can come up with the solution to this problem again and write it up, maybe I'll do it in a future video. But that's how you do it. You essentially recreate the proof of Schwarz's lemma, but you need to use a specific function, and you need to use something that's inspired from here. And then the answer just fell out in front of me. Like, when I got to the end, I was so happy when I saw that I finished the proof by drawing a... You know how when you finish a proof, you put a box at the end to let the reader know the proof's over? I used a smiley face at the end because of how happy I was. So I knew what I had written was correct, and I got full credit on it. So maybe partial for 1, and then I definitely did 2, 3, 4, and 5. And knowing how this guy grades, I was not told my score, by the way. I just told that I passed. I believe my score was probably in the neighborhood of 70%, maybe as high as 75, if I had to estimate. But I don't really care about the score. I'm just happy that the whole thing's over and done with.